All right, students, let's go through the solutions here. This will be a good chance to learn from your mistakes and also to kind of self-grade, kind of know where you are and how you stand here on exam number 3. All right, let's give this one a try. We have a toroid, nice little picture with a rectangular cross-section. And so here's the cross-section of dimensions A by B, and they give us A is 2, so maybe I'll put a little 2 right here, and B is 3. Has an inner radius of 4, inner radius of capital R equaling 4 centimeters. The number of turns is 320, and has a current I, which is 12.5 amps, and then has a frequency of 60 hertz. What is the voltage it induced, and it'll be a function of time, in the secondary? All right, well, hopefully this sounds exactly like Faraday's law that says an induced EMF is connected to the rate of change of the magnetic flux through that loop. And so that loop would be this N prime, this secondary, which said it had a number of 52 little loops here. And so we're after this voltage V here, and so I'll just leave the negative alone and put 52. This would actually be the N prime. This is the N for the number in the secondary. The flux itself comes from the current in the toroid. And so you can kind of see that this problem is a blend of chapter 30 and 31, because in 30, we learned what the magnetic field is from a toroid. That was Ampere's law. And now we're going to apply that to then this toroid here. And so we've got a little flux calculation to do. And fortunately, this flux calculation is pretty straightforward. The magnetic field is the Ampere's law that depends where you are measured by R, and there's the little r as measured from the center of what I call the donut hole. Okay. Then we got our dA, and we should probably put in cosine of 0 degrees. And of course, to understand that, we would have to, again, go back to chapter 30 and make sure we understand that the magnetic field is in the tunnel part. And so the area of this secondary vector would be, of course, in the same direction. Maybe I'll put area vector here in the blue. And so as the magnetic field comes around, the magnetic field and the blue vector are in the same direction. So that's cosine of 0. I'll put the minus 52. Maybe I'll spread this out. We've got a derivative with respect to time and an integral over space. And so N here is from this primary, so I'll move that out front, 320 here. The mu naught is the permeability of free space, and so I'll just kind of assume, as it's kind of indirectly implied here, that the core of this toroid is just empty space, and that's all we've been doing this semester, or at least mostly we've kind of touched on that. So I think that's a fair assumption. And if you remember, that is 4 pi times 10 to the negative 7. I say that because there's a 2 pi down here. So if we write this then as 2 times 10 to the minus 7, that would take care of the mu naught and the 2 pi. Now, the current changes with time, so I cannot bring it all the way out in front of the time derivative, although at a given instant in time, the current is constant over the space of the over space, which would be the calculation of the flux here. So I could argue that the current can be moved in front of the integral sign, but not in front of the time derivative. Of course, that still leaves the 1 over r back here in our integral. And a dA would be the area if we were like taking, and I guess I'll do it here, strips. And we look at one of these strips, it would have a height of A and a width of dr. So this would be A dr. And so that would be the integral of the area. All right, so let's see what we got so far. We got the minus, we got the 52, we got the 320, we got the permeability of free space, and also the geometry of the 2 pi for the toroid. And then maybe I'll go ahead and take the derivative of the current, because the derivative of the current, of course, I would still have my 12.5. But derivative of sine is a cosine. Cosine, let's see, sine would be what? Yeah, so cosine. And then the chain rule would give me the omega. So there's the derivative of the current. And then this integral, of course, the A, which we said was 2 centimeters, so I better watch my units here and write it as 0.02 meters, is a constant, and I can bring it in front of the integral. And then the integral of dr over r is a natural log, and we would be adding these strips from this inner radius, so from capital R to capital R plus b. And of course, capital R is 4 centimeters, and B was 3 centimeters. Yeah, so this would be 7. So this would be the natural log of 7 over 4, which, if we wanted to be a little careful with our units, we might write as 0.07 over 0.04, but it's still the same ratio. So there's no point in converting that to meters, or it's not necessary, but maybe just for clarity. And now it's just plug everything in. Of course, we are going to have this cosine of 377t left over. So that's our function of time. And so I guess technically a negative. And now we've got to put all these together. And so the turns in the secondary, the turns in the primary, the permeability of free space, the amount of current, the rate of change, and then the geometry of how big each of this rectangle is, 0.02, and it's not really the dimensions of the geometry because this is an integral, but it is this natural log of 7 over 4. And I think I put all that together successfully. And so this is 0.17, I'll call it a 6, and this would all be in volts. And so there would, I guess, be the answer to number 1. What is the voltage induced as a function of time? And so there is this phase shift that, of course, we saw with the AC circuits, and I'm pretty sure there's a problem coming up here with the AC circuits. But there is our current coming in as a sine function, our voltage being induced in a secondary. So cosine, same rate of change, and then this is the voltage produced. Yay! All right, so hope you did well on that one. Let's move on then to our circuit stuff. And here we have a little bit of a complicated looking circuit. Oh, looks like my red ink bled through here. I wonder if I want to keep doing things in red. Maybe I'll keep the red for a special occasion. I'll go over to the blue here. But here we're going to close the switch. And so it says study the circuit on the right. And so as we study it, it looks like we have 2 inductors that are in parallel with each other, 2 resistors that are in series with I guess I'll just say with each other, but also in series with this group of parallel. I suppose we could write this, because I think this is coming to a point where we probably want to write this as the equivalent resistance and the equivalent inductance. Now, I'm just going to guess that, but let me keep reading here. They give us the voltage. They give us the values of the resistor. They're identical. They give us the value of the inductors. They're identical. And the first part of this says, what is the current through the switch S the moment the switch is first closed? And you could look at this equivalent, or you could go back to this real thing for this one. Hopefully this one is straight forward enough. But we did argue that there would be a back EMF as you tried to change the current. And so if you're plotting current versus time, and you had no current, and then you close the switch at time equals to 0, it wouldn't just pop up to some new value, because that would make a derivative that's infinity, and an infinite derivative would create an infinite voltage, which would, I guess, have so much voltage back the other way that you close the switch and the current would actually go an infinite the other way. That makes no sense. In fact, we argued that the energy in the inductor, 1/2 Li squared, so when you take its derivative, the rate of change of the energy, would be 1/2 L2I dt. And that was another part of this argument, that you couldn't really have this instant change in current, because if that goes to infinity, that requires an infinite amount of power. So unless this power supply had an infinite amount of power, which it doesn't, you're not going to change the current instantaneously. So the point is, right after you close the switch, there would still be 0 current through our inductor. And that was our argument, that the change could not be discontinuous. It would mean it would have a derivative that's infinity, which takes an infinite amount of power. In fact, what the change of current would have to be is just enough to have a back EMF equal to what's being pushed, which in this case is 12 volts. And so at this particular instant, when you close the switch, there would be a back voltage of 12 volts here. And so as you add up around the loop, there would be no voltage for here, which would mean 0 current. And that's what we mean here when we say the current wouldn't change instantaneously. That is, if it was 0 right before you close the switch, the inductor is going to do whatever it needs to do with the change in the current in order to get the current to still be 0. And so that was just a long way of saying one of the properties we learned in this argument was that for inductors, they act as open switches the moment you hook them up. And so when we close this switch, they act as open switches. And so you could think of this at this point as something that looked like this, a 12-volt battery with an equivalent resistor, and then the inductors are an open switch, which means you would get 0 current. So maybe I said too much. You probably already knew all that. At least that was hopefully the argument of this mini lecture of how we treat an inductor the moment the switch is closed. So what is the current through the switch, which when you look at the equivalent, that could have said the current through the battery or the switch or this top resistor or the bottom resistor, since they're in series. Now they do divide across here, so we'd have to be a little careful if they ask for the current in here, but all of these would be the same thing, whether they ask for the current in this resistor, the battery, or the switch. They're the same branch. So what is the current through the switch S the moment it is first closed? Well, we're going to treat it as an open circuit. And by the way, that same logic said after a long period of time, things settle out, and you don't get any voltage. And you can see that in the math for the inductor. The voltage in the inductor is minus L di dt. And so after a long time, with a DC circuit, I should point out, the current doesn't change anymore with time. And, that could take a couple of seconds for some long circuits. Most of it is, a couple microseconds. But this just stops changing and you don't get any voltage. And so that's why we argued that after a long period of time, you could argue an inductor is just a wire, no voltage change at all. And so we call that a closed circuit. And so looking at this equivalent one and just making a line here, then the current would just be the voltage divided by the equivalent resistance. Now the voltage is 12 volts, and the equivalent would be the two resistors in series with each other. And so that's 200. So that would be 6 divided by 100. So 0.06 amps, or if you like, 60 milliamps. Yay. All right. So there is I think the easier of the problems. Again, this is what we learned about our inductors in a DC circuit is, when you first close that switch, they act as an open switch. Then after a long period of time, they act as a closed switch. So what is the current through the switch after the switch has been closed for a long time? All right, then C, it says, what is the current through the switch 50 microseconds? Well, it's not required for you to go through the math on this because we did it in class where we said, okay, take the voltage 12 minus IR minus L di dt equals 0. And then when you solve this, you get the current is equal to, and we came up with something that looked like the same formula we got as we were charging up a capacitor, although the capacitor had charge on it instead of current. And so we like to say we're energizing these inductor. Now, of course, we did this little equation for the equivalent one because it had one resistor and one inductor. And so let me think about this being applied to the equivalent, and then eventually we'll make the step up here that says, well, okay, what does this do for the real circuit? But applying this, we can see then that I naught is going to be what we got in B, the 60 milliamps. This is the current after a long period of time, right? After time goes to 0, this goes away. And so this is the long-term current, the V over R. And then the time constant is the L over the R. Now, since we have more than one inductor and more than one resistor, the work that we did was associated with just one inductor and one resistor. So let me apply this to the equivalent circuit before we go back to the real circuit. But when I have two in parallel, inductors, if you remember, add like resistors. So this would be 1 over L plus 1 over L is equal to 1 over the equivalent of L. Or 2 over L is 1 over the equivalent. Or put another way, the equivalent is L divided by 2. Okay, so if I take this L and divide it by 2, so L is 10 millihenries, I'm going to have 5 millihenries for the equivalent inductance. And the resistors are in series, and so we add those, and so 100 plus 100 is 200, and that would be 200 ohms. And let's see, I guess 5 divided by 2 is 2.5. And we already have 10 to the minus 3 in the 100 down here makes 10 to the minus 5, which I'm going to write as 25 micro. And I suppose we should take a moment and look at our units. But remember, Henry is the voltage you get when you are changing it at an amp per second. So I'll put the per second on top. That'll be helpful because an ohm is a volt per amp. And see, the volts per amps cancel off, and you're left with just second. As we should be. It's a time constant. So 25 microseconds. And so this problem asked for 50 microseconds. So in other words, T over tau, which would be 50 over 25, which is 2. So that means this up here is a negative 2. All right, so to put in our numbers here, so the current would be, and so right here is my 60 milliamps, and then 1 minus e to the negative 2. So 2 time constants. All right. And so grabbing my calculator here, if I go e to the negative 2, and so now if I go 1 minus that last answer, looks like that comes out to be about 86%. So it looks like it has built up to about 86% of the eventual long-term current, which would make it about a 51.9 milliamps. So 2 time constants. It's getting close, but not quite there to the full current of 60. So hope that helps. Okay, so with that said, let's move on to number 3 here. Okay, so number 3, again, we got another circuit. Actually, I guess if I was labeling this is applying our induction, so our Faraday's law, chapter 31, to our circuit. So this is chapter 32. And then we do this again in chapter 32. So these are both 32 circuits, a DC circuit. But this, you can see, is going to have some capacitors and some inductors. It's going to have some oscillations. In fact, just kind of looking at it, that's what it says. Study this circuit on the right here. But I would have my resistor, my switch, and I have a capacitor and an inductor. If I put here the equivalent capacitance and the equivalent inductance. Now they give me the value of the voltage, looks like 9 volts. Oh, by the way, should I come back here? I probably should have made a comment. I just realized as I was making this equivalent circuit that technically what I just did was everything for the equivalent circuit. And so coming back up to the real circuit, the current coming out of the battery in the equivalent is the same coming out of the battery in the real circuit and the same going through the switch. And since they asked the current through the switch, I actually finished the problem. If they had asked something about the current in the 2 inductors separate, then I'd have to figure out how the current in this equivalent inductor got divided between those 2. And since they're identical, it'd be a 50-50 split, so it wouldn't be real hard. But I probably should just make that comment. That's, okay, this really was the equivalent circuit, but it is also the number we need for the real circuit. And that's what I started to think about again here on this one, that we have this equivalent circuit, and we're going to study it and use it And of course, it's going to lead us back to this one. But I was just looking ahead here, and it says, what is the voltage maximum? Let me fix that. Across the top resistor. And so let's go ahead and do the equivalent circuit, which will do this equivalent one, but then we'll have to kind of come back to the real circuit. So anyways, getting ahead of myself here, but they give us the voltage, they give us the resistance R here. Yeah, I think that's good. I was thinking maybe that's a little too low, but I think that'll be good. They give us the capacitance, they give us the inductance, and then and here's the big key: the switch has been closed for a long period of time. So when the switch has been closed for a long period of time, we could think of this, and it's kind of back to problem number 2B. After a long period of time, we can think of the inductor as just a closed wire. And so after a long period of time, maybe I'll just put another little circuit here. Here's the R. The capacitor would fill up and act like an open switch. And the inductor its voltage would go to 0 because the change of current, di dt, so it would be a closed switch. And so this would be 10 ohms and 9 volts. And this is what we would have after a long period of time. So when they tell me the switch has been closed for a long period of time, I'm going to conclude that the current coming out of the battery and going through this resistor, and then nothing going into the capacitor, and all of it going through the inductor, is equal to V over R, which would be 9 over 10, which would be 0.9. And so that's what I would get out of this first piece of the question, okay? See, but then the switch is opened. And so when that happens, now I have a circuit that coming back up to here basically means the battery and the resistor and all that's gone, and I just have an LC circuit here. And that LC circuit then is where we would get our oscillations. And you might remember us doing a problem in class where we started with a charged capacitor and then fed it into an inductor. In fact, I even hooked it up on the oscilloscope so you guys could see the oscillations. And so if we plotted, say, the voltage on the capacitor versus time, we saw that the way I hooked it up was the capacitor was charged, and in a perfect world it kept the same voltage back and forth, and in the real world we saw it kind of taper off there a little bit. This one's a little different because we're not starting with a charged capacitor. We're starting with a inductor that has a current, and so maybe we would plot the current that would start within the inductor, and then it would oscillate because the energy source is coming from the inductor here. That's the idea here, and so that's what I guess I want to emphasize for this one. But in either case, whether we start with our energy stored in our capacitor or in our inductor, we said that the angular frequency would be the square root of L over C. And the angular frequency is then 2 pi times the regular frequency. All right, so in our case, our two capacitors are in series, And so to get the equivalent, we have to do, again, this 1 over C plus 1 over C equals 1 over the equivalent, or 2 over C is 1 over the equivalent, or the equivalent is C divided by 2. So as I look at this equivalent circuit and put down here equivalent inductance, equivalent capacitance, I got a 1 over the square root of, and I would have a 0.5 microfarad for the equivalent of these two capacitors that are in series. And likewise, the inductors we would just add together. Let's see, and they're 100 millihenries. So if we add them together, we would get 200 millihenries. And so taking my calculator, 200 milli times a half a micro, that would be the L times the C. And if I then take the square root of that and then the reciprocal of that, I get an angular frequency of 3,162, and then a regular frequency, we divide by 2 pi, so divide by 2 and also divide by pi, and we get about 503 hertz. So 503 hertz. Yay! Which, by the way, is the same number. In fact, these numbers are the same in the lab this week. So if you've done the lab or you're about to do the lab, you'll see that we have a circuit that resonates. Yeah, maybe I should be real careful. The one, because we hook up an AC circuit. We don't really do this, but it does have the same resonant frequency. So never mind what I said there. That's probably best to save those words for the resonant circuit that we're going to see with the AC circuit coming up in step 4. All right, but there's the answer to A. I guess I need to box this. Okay, so here is A. What is the frequency of oscillation? And then B, during these oscillations, what is the maximum voltage across, and then just the top capacitor? So before I jump back to the real circuit, again, let's talk more about this equivalent one. And then we could say something like this, that the energy as it goes back and forth at any moment in time, some of the energy is stored on the capacitor, and some of the energy is stored in the magnetic field of the inductor. So this would be storing the energy electrically, and this would be magnetically. And the analogy we used in class was kind of like a pendulum going back and forth, or a mass on a spring going back and forth. And there's these two energies. In that case, it was kinetic and potential energy. And of course, at any given moment, all of that would add up to a constant. And so I'm thinking maybe the best way to handle this one is to say, something like at time equals to 0. And so that is right as we begin to open the switch. And we're looking at something like this. Since this is just a wire, we can say that there would be no charge or no voltage on the capacitor. And the current is 0.9 amps, which is what we worked out here in this circuit. And the equivalent inductance is the 200 milli. And if it'll be okay with you, I'm going to just go ahead and write the 200 milli as just 0.2. So 0.2 henries and 0.9 amps squared. And so I know what this constant is. 1/2 times 0.2 times 0.9 squared. And so this is the total energy, I guess it would be joules, in the circuit, which I'm calculating right as the switch is opening. But as the energy gets fed from the magnetic field of the inductor into the electrical field in the equivalent capacitance here, all of this energy then eventually would go into the 1/2 CV squared. Or maybe to put another way, when you get your maximum voltage, the capacitor is fully charged and you would have zero current. So at some other time later, and I guess it'd be about a quarter of a cycle. And so a quarter of this, let's see, 225 reciprocal of that. 503 reciprocal. So the total time is about a 0.02. So if I take a quarter of that, okay, so about, I'll call that 5 or 0.5 milliseconds. So the time's not important, but at about 0.5 milliseconds later, all the energy has transferred from the inductor, so now there's no more current in the inductor, and it's all gone to the capacitor. And that's where you're going to get your maximum voltage. And so that's why I'm going to set then the 1/2 CV squared maximum to this constant energy of 0.081 joules. And what did we say the equivalent capacitance was? A half a microfarad. And so this will give us a chance to solve for the maximum voltage. And let me not forget, this would be the maximum voltage on the equivalent circuit. We still got to come back to the real circuit here. But if I take that 0.081 and let's see, multiply it by a 2 and then divide it by a 0.5 micro, that would be the voltage squared. So if I take the square root, we're looking at about 569.2 volts. Which, by the way, is quite a bit of voltage. You can see why this opening of switches like this can be both a blessing and a curse. If you have something with a lot of inductance and you just go to open a switch, or if you have a electric motor, which isn't designed necessarily to have a lot of inductance for inductance sake, but it's there because you have a bunch of coils to make a strong magnetic field, and somebody unplugs it on you. Ouch. That can produce a lot of back EMF and wear out the motor, even turning it off. But then turning it off, you can do some kind of short circuit resistor here that kind of absorbs that energy. Unplugging it, though, you have other issues, but you could throw in things there. But you can kind of see, if you hadn't already seen in our circuits, that from a practical point of view, these inductors can be really nice. They can really blast and open up the voltage to values that you would not normally see. I mean, normally, right, we're just having here a 9-volt battery. I mean, this could be, a taser. You put a 9-volt battery in there, and then we have oscillations that then create huge voltages. And so in that case, we would want the huge volts for our taser. But on the other hand, we wouldn't want that high voltage if we were just unplugging or turning off an electric motor. That could do some damage. I guess it also is a good thing for you guys going in electrical engineering. Why? To make this capacitance, we'd usually make it out of a stack of a bunch of capacitors. We might think of it as one capacitor when we analyze it, But applying 500 and almost 70 volts to one capacitor is usually way too high. You remember the capacitors I blew up in class, had things like do not exceed 25 volts or something like that. And so this is just way above that, which is why then the final question about how much is on just the top capacitor, I can just say, well, the voltage is, total over the two, and so it's split in half. And so this is 284.6 volts, which still is a high voltage. So you could imagine that if I was really building this taser, I probably would want it portable, so I probably would use a 9-volt battery. And I probably then would have a switch that would, open and close, so this would go on relatively frequently. Probably would want it to go higher than that, so I would, probably have a different value for my inductance and my capacitance. But I probably would have a whole stack of these, maybe a stack of 10 capacitors, so that this whole thing is then divided by 10, and we're only then looking at about 57 volts per capacitor, which still might be a little high. So maybe I'd have to go a little bit higher depending on my equipment I had to purchase and where I was getting my voltages. Anyways, I'm getting off the main topic here of this little LC circuit here, but that's then the answer to the question. During these oscillations, what is the maximum voltage across the top capacitor? So, nice. All right, well, another circuit one. I think our last of our circuit one. You can hopefully see this from chapter 33. We have our AC circuit. Looks like it feeds into a little transformer. And this is kind of interesting. Looks like it feeds through a resistor, a capacitor, another capacitor, and an inductor. And this doesn't go anywhere. So it looks like with the switch in position A, we can kind of just ignore this inductor. And the reverse is true, that if we move this switch over from A to B, it looks like now it'll go through the resistor and first capacitor again, but now it'll go in series with two inductors and completely eliminate the capacitor here. So we can change something. Something's gonna change here on this switch. And the transformer, as the name implies, is going to transform the voltage here. I have a feeling here. But anyways, I'm doing this first part. It says study the AC circuit on the right. So, all right. So I kind of studied it on the right. They gave me the resistance, 1,000 ohms. They gave me the capacitance of 1 microfarad, and each of them are 1 microfarad. The inductance is 900 millihenries. So pretty good size inductors. So I'm going to put two of them together, I think, eventually. The maximum voltage from the power source is 10 volts. Now keep that in mind, the way it's phrased there. The 10 volts is the maximum. It's not the RMS, and it's from the power source because it's going to get fed to this transformer. Yeah, so this is fed from a transformer which has 90 turns in the primary and 180 turns in the secondary. So this is what we call a step-up transformer. That is, it's going to increase the voltage. With the switch in position A, so as shown in the diagram, the current and the voltage are in phase. That's a good giveaway there. And then two questions here. What is the frequency of this AC source? And what is there it is, RMS current. Yet they gave me maximum. Okay. Well, let's start here with A. And for our AC circuits, we learned, it says, what is the frequency of the AC source? This is really kind of nice because if you remember, the phase phi is XL minus XC over R. And so if they're saying they're in phase, that means we have tangent of 0, which is 0. XL minus XC over R. And that means XL equals XC. So the reactance of the inductor is equal to the reactance of the capacitor in this situation right now, where we are at switch A. And so we have omega L for the reactance of the inductor and 1 over omega C, or put another way, omega is 1 over the square root of LC. And so in this, what we'll call the resonant frequency, the magical frequency, this magical frequency is, what we get when the inductor and the capacitor just match naturally. And so not a surprise that the equation, as they would self-oscillate, as we did in problem number 3, has this same frequency as their resonant frequency. And so that just means it works best at this particular frequency. Everything's in phase. You're getting the most current from it. We don't have to be exactly at that. And you're going to see it's going to change when we get to B. But this is its natural frequency, if you will. Okay. And that really helps because we're trying to find this frequency. And so I'm going to go 1 over the square root of L. And as I look at it, going through B here, it goes through 2 capacitors and 1 inductor. So the L is this 900 millihenries. And if it'll be okay with you, I'll put the 900 milli as just 0.9. Now, the C, we got to give a little more thought. We've got 2 capacitors, 1 microfarad each, and they're in series. And that does give us the same thing in step 3, where we concluded that the equivalent would be half of that. And so thinking of these 2 as 1 capacitor, I would have a half a microfarad. And so this would be the angular frequency. Okay, so 0.9 times 0.5 times 10 to the negative 6. And then if I take the square root of all of that and the reciprocal, I get 1,490.7. Or to answer the question then, the frequency, which is omega over 2 pi, would go then divide by 2 and divide by pi. And so the frequency of our source at its natural, because it is at its natural frequency, and so I can calculate its natural frequency, is 237 let's go 0.3 hertz. Yay! Okay, and so there is the frequency of my AC source. Now, B says we do this. It says, what is the RMS current when the switch is moved to position B? All right, so now we're going to go over to B, and when we go over to B, of course, we're going to lose a capacitor and gain an inductor. And that, of course, means no longer are these two going to be equal. I guess that also means there's going to be a phase between the current and the voltage, but they didn't ask for that, so I guess I won't worry too much about that. But I'll go ahead here and do a impedance calculation. Maybe I'll start with XL. But then I'll also do an XC. And the R, I guess I don't need to do any calculation for. That's 1,000. Okay, but the frequency won't change when I move the switch from A to B. That's the driving frequency here of our oscillator. So this is still a 1,490.7 for the omega. But what will change is my inductor will now be two of them together, and each one is worth 0.9. And so this is going to be 1.8. And so the reactance I get would be this times 1.8. And so it looks like 2,683.3 ohms would be the reactant from the inductor. Now, for the capacitor, we're only going to go through one capacitor now when we're at the switch B. So my one capacitor would be my 1 microfarad. And then my omega is the 1490.7. And if I take the reciprocal of that, we're looking at only 670.8 ohms. So again, notice they're not equal. And of course, notice what happened when I move it from A to B. I'm going to get more inductance. So this one goes up and less capacitance. So, or excuse me, more capacitance because they're not in series anymore. And this one, then more capacitance goes down. Now, my impedance then is the R squared plus the XL minus XC squared. So why don't I do the XL minus the XC? So, because that's kind of easy to do. There's the XL minus the XC. So a difference of about 2,000. I'll square it. Add that to the R, which is 1,000 squared, and then take its square root. And so together, all the elements are impeding the current by what would be 2,247 ohms. And so there's a blocking of the current due to the inductor, the capacitor, and the resistor. That's because the current then for an AC circuit is the voltage divided by the impedance. And of course, here's where we got to be a little careful with maximum and RMS. They go together. So maximum voltage goes with maximum current, and RMS voltage goes with RMS current. And this problem clearly asks for the RMS current. So the RMS current would be the RMS voltage divided by this impedance of 2247. But here's where we got a little bit of work to do also, because we know that the voltage, maximum voltage, is 10 from the source. But if you'll notice, we talked about this transformer, and so it starts at the source, but it gets boosted up by a factor of 2 to 1. Remember, the voltage in the secondary is the voltage of the primary multiplied by the ratio of the turns between the secondary and the primary. So 180 over 90 times the 10 is 2 times 10. And so what I'm saying here is that the peak voltage of 10, the maximum voltage of 10, now becomes 20 after running through that transformer. But then we got to divide it by the square root of 2 in order to get the RMS value. So this would be, actually I'll do it this way. Square root of, these two together make the square root of 2 times 10, because the square root of 2 is 1.41, so this would be 14.1 volts divided by 2247. All right, so 14.1 divided by the last answer is about, and I'll do milli, so this is about 6.27 milliamps. Yay, after all that. So it's a good, hard problem there. So hopefully you got those. So these are some hard problems. I hope you're doing well, and I hope you're learning something along the way, not getting frustrated. These are hard. And here's the last one, and I did tell you that this would hopefully be a straightforward question. We didn't have much time to go too much detail, so I tried to kind of set up some straightforward problems here, and there are the 4 that I said I would give you. And so we're going to look at some communications, air-to-air communications of some pilots. And there's a whole frequency range that the airline pilots can use. But one of the ones they like is called the fingers, because they can just count it out. 1, 2, 3.4, 5. And megahertz. And so if we send a message, so if a pilot sends a message to another pilot, which is 25 miles straight ahead, which straight ahead we'll call the x-axis, and it has an antenna, it's a magnetic antenna, and it creates a magnetic field in the y direction, and it gives its strength. What direction is the electric field? Well, hopefully, as we worked out in class, we had this kind of in class, where if we had the electric field in the y direction, and the wave traveled then in the x direction, the magnetic field would be in the BE, in the z direction. And that's what we worked out in lecture, and this is almost the same thing. The difference, though, is we now have the magnetic field in the y direction, and we still have the wave, though, traveling in the x direction. And so the point of the lesson was that the electric field, magnetic field, and direction of travel make up the 3 Cartesian axes. And so we do want to get the order straight. And so if the B field then is going to be, so here's the magnetic field, is going to be the y direction. Maybe you can imagine kind of rotating the B field up like this. So now the B field is here. That would make the y, the electric field, which is in the y direction, would now be in the negative z direction. And so I guess negative z direction is the answer that I'm looking for. And since it oscillates, I guess technically the negative is not really important, because the B field's going to go plus or minus, and then the electric field is going to go plus or minus. But when the B field is positive y, the electric field has to be negative z. Now, a moment later, that's going to change, because the B field is going to be down here, negative y direction, and so the electric field is going to be positive z. So it's best if you put negative z direction, I think, by the way it's phrased, but I'll just take z direction, trying to get the idea that we got all three dimensions involved. The x dimension is, in this case, the direction it's traveling, and then the magnetic field is the y direction, so then the z direction must be the electric field. And that's what this is. What is the direction of the electric field? Okay, now B, what is the strength of the electric field? And so as these were induced from each other, the B field induces the electric field induces the magnetic field. There is a nice ratio of the speed of light. And, well, I guess that's also 1 over the permeability and permittivity of free space. So you can do it this way or go right to the speed of light here, the speed of radio waves. But this would say then the electric field would be the magnetic field times the speed of light. So taking the magnetic field to be 4.55 times 10 to the negative 10 and multiplying it 3 times 10 to the 8th, this would give us a electric field strength of about 0.13, and I'll round up to a 7. And the units, I'll use volt per meter. That's kind of nice, especially when working with antennas. So if the receiving plane had an antenna that picked up on the electric field versus a magnetic antenna, it would produce 0.137 volts if the antenna was 1 meter long. If it was longer than 1 meter, well, we'd get more than that, and less than 1 meter, we'd get less than that. And some other complicated things going on, but that's roughly an idea of the strength of the electric field. Okay, C, what is the wavelength of these radio waves? Well, speed divided by its frequency is its wavelength. So let me go at speed, 3 times 10 to the 8th. And its frequency is 123.45 megahertz. And so we're looking at a wavelength of about 2.43 meters. And then D, how much time does it take? Well, this really is part of Physics 121, where there is a relationship between speed, time, and distance. And so for after time, it would be distance divided by velocity. In our case, the velocity is c, the speed of light. And the distance, we got a little bit of unit conversion. We know it's 25 miles out, but of course, each mile is worth 1,609 meters. So multiplying those two together would give me meters, and then divided by meters per second is going to give me so many seconds. So 25 times 1,609, and then divide that by the speed of light, or the speed of radio waves, or the speed of electromagnetic waves, and we get 1.34 times 10 to the minus 4 seconds, although maybe I'll write it as 0.134 milli. Move that, let's see, that gets smaller, so that has to get bigger. Yeah, milliseconds. And so how much time does it take to travel? All right, good. Well, I hope you did well, and hope you learned a few things from this. Take care, everyone.